Okay, so this is mostly work that, I did over the last couple of years that was published last year. At the very end, I am going to show some fun work in progress, extremely preliminary, as in plots that were made earlier this morning, type preliminary results from upcoming work, and that'll be at the very end. So the story I'd like to kind of tell in the kind of canonical picture, or maybe now what we might call the old picture of galaxy formation. You have some kind of proto-galaxy at higher redshift. You have gas inflow from kind of all over the place. All the gas shock heats. The gas comes in with the same angular momentum as the dark matter, set from tidal torques on large scales. All the gas shock heats, it kind of mixes in the halo, just like the dark matter mixes in the halo. And so you still have kind of this same angular momentum distribution of dark matter versus gas. Well described by the halo spin parameter, lambda, and then eventually some cold gas kind of cools out of this hot halo, and if you kind of keep track of the angular momentum and you look at the spin parameter of the dark matter, and the gas conserves angular momentum as it falls into the galaxy, you get something with kind of maybe just enough angular momentum to support a disk rotating galaxy, and this was kind of the picture we had in mind for how galaxies form. Now the problem is, a couple of problems with this kind of older picture. First of all, we know from simulations that's not how it works anymore, or we believe so anyway. A couple different scenarios. At high redshift, even if you have a massive halo and you used to think that everything's shock heated, we now know about these cold flows, cold mode accretion, and the gas is dense enough to stay cold and kind of penetrate all the way into the galaxy, so you don't have this mixing in the halo for longer time periods that you used to think that you had. You also have it kind of lower masses, kind of at all redshift, you still have this cold mode accretion. So this picture we have of the gas kind of acting the same way as the dark matter and having the same spin as the dark matter doesn't really apply anymore. A couple more cuts kind of from the theory side. Observationally, there's been some observations of kind of more extended disk-like structures. So for example, from the Things survey here, you have a galaxy in kind of the H1. If you look at the size of the Milky Way versus the size of these things, they are huge disks requiring much more angular momentum. And so if you just had barely enough angular momentum in this old scenario to build a disk, and now you want to build a gas disk like 2 or 3 times as big, how can you possibly have that much angular momentum in your material? It just doesn't work if you start from the presumption that like all the gas has the same angular momentum distribution as the dark matter in your halo. It just doesn't work to build these things. The kind of more recent motivation from my own work, for a few years prior, we were looking at our simulations, and we looked at, this is the spin parameter in particular, but you should think of it just as angular momentum, as a function of time in one of our galaxies. And we see that, yes, the dark matter kind of wiggles around a roughly constant value. We've known that for a long time since n-body simulations. But if you looked at the gas in the halo, so not kind of blocking out the galaxy and just looking out in the halo out to the virial radius, the gas had much more angular momentum than the dark matter does. So you have kind of all the hot gas, kind of all the gas global average, just the cold mode gas, and you have much more angular momentum in the gas. So clearly, I mean, this should help in building these extended disks, but what's going on here? The old picture doesn't work because the gas is not doing the same thing as the dark matter. And so what's a better way to think of this? And that's kind of the goal of the paper we put out last year, studying the angular momentum acquisition in 4 zoom in, what was at the time high resolution simulations, and asking the following questions. How does the angular momentum buildup happen in the galaxy? Now, mostly we're looking at the halo. We don't want to try to say too many very strong statements about the galaxy itself, just for a matter of resolution in our feedback scheme that we have, which I'll talk about in a second. But in the halo itself, so when you're talking about like entering into the virial radius from the cosmic web, what's going on in terms of the angular momentum? Is there a difference between what the cold and hot modes of gas accretion are doing in terms of angular momentum? And therefore, is there kind of a more consistent model for how galaxies and galaxy halos in particular acquire their angular momentum? And this is all work that a number of other great teams are doing as well with very complementary, similar results. Kim et al. Also has a paper, Avishai's talk the other day. They're finding similar things to kind of what I'm going to be saying today. So here's a pretty picture of a couple of our simulations, kind of zooming in. And now we're looking at things that end up as Milky Ways today. So we don't have the supermassive, living at a node where 3 or 4 streams all come together. These things kind of just sit in a filament. They're not quite as high mass and high kind of density peaks at high redshift. So more likely kind of sitting in a filament that's kind of flowing it from both sides rather than sitting in a node with lots of different streams intersecting. Roughly Milky Way size things, gas resolution, the spatial resolutions of a few hundred parsecs. These simulations are a few years old at this point, which again is why we're going to focus on the halo and not the specifics of the inner workings of the galaxy there. We also, so for this resolution and the kind of feedback scheme we don't have super strong outflows and winds, which is just to say things will probably get messier and more complicated as you have more realistic feedback schemes. So what I'm going to be talking about is basically just inflow. What is a cold mode gas doing as it comes in? Things might get muddied a little more if you then add fancier feedbacks with outflows and all this extra stuff. But one step at a time. Let's see if we can at least understand what the inflow is doing, and then we can worry about complicating it with extra outflows. So just a reminder, the spin parameter is defined as a specific angular momentum normalized by kind of the circular velocity at some radius, and that radius. So typically this is defined for the entire halo when you do the circular velocity at r-vir, and then you plug in r-vir. Before we even talk about the simulation, just a little thought experiment here to kind of wrap your mind around what this parameter really means. Now, n-body simulations have shown for a long time that if you look at dark matter halos, regardless of basically what mass scale you're looking at, and with some amount of scatter, you find roughly constant spin parameter of lambda about 0.04 for dark matter halos. But let's think about what that means for a second. Let's think about one individual dark matter halo or one galaxy as it's progressing over cosmic time. How are these parameters going to change? Well, the galaxy is going to grow. The circular velocity is going to grow. The virial radius is going to grow. And we're saying that all the n-body simulations say lambda stays the same. So kind of without even doing any real analysis of your simulation, just looking at this equation, you can know that newly accreted material has to have a higher specific angular momentum. Because if you keep normalizing by a bigger and bigger denominator there, and the lambda stays constant, then kind of right out of the simulations before you do any gas physics, the newer material is going to have a higher specific angular momentum. And there was some great work, Kim et al. Looking at kind of the details of why this is so. It has to do with kind of the tidal torques that turn around and which material is coming from where and all that great stuff. So just something to think about there, that this angular momentum, the specific angular momentum is going to grow over cosmic time, kind of by default. You can't get around that. So what we did, we looked at the angular momentum. This is kind of a track over time for one of our example galaxies. So it's in look-back time, so early universe is on the left, and it's moving towards present day as you go to the right. The various lines, I know there's like a million lines on this plot, so just bear with me. The black is basically the dark matter. The green kind of dotted curve is what you would get when you presume this kind of just constant spin parameter for dark matter of lambda 0.04, which we know shouldn't be horribly wrong based on in-body simulations for a long time. And you see they roughly track each other. The red is for hot mode, and the cold mode is in blue. And this is just looking at everything in the halo. We're kind of cutting out the central galaxy region because we just want to know about kind of more the outskirts of the halo. So everything from about 1/10 of the virial radius out to r-vir. And what we see is, well, yes, the angular momentum of the galaxies is growing over time, which is kind of necessary if your halo is growing, but you're keeping the same spin parameter. But note that the cold mode gas in the halo is higher than kind of everything else. So it's something is happening here. Something different is happening with the cold mode gas in the halo. Now you can compare that. What if we just look at stuff that's falling in right now? So we can look into our simulation, pick out all the particles that have fallen in the last 300 megayears or so. And so you're looking at just fresh accretion here. Note that all the curves are higher. So even the dark matter, necessarily, stuff that's falling in right now has more angular momentum than kind of the global average for the whole halo. Not surprising there. And again, you can kind of parameterize that. If you pick a constant spin parameter, but you pick about 0.1 this time instead of 0.04, then that kind of roughly captures that green line, kind of what's the spin parameter of dark matter that's falling in kind of right now as a function of cosmic time, which I think Avishai found something very similar, spin parameter about 0.1, like right as it's falling in, rather than 0.04 for the global average. But again, the cold mode gas is just systematically higher than kind of everything else. So something's different about the cold mode gas in terms of its angular momentum content compared to the hot mode gas or kind of the global average or the dark matter, even when you're looking at stuff that's coming in kind of right now, just very recently. There's something different about the cold mode gas. It has more angular momentum, whereas the hot mode and dark matter are kind of comparable to each other. We did a similar, so you look at kind of very fresh accretion, a global average. You can also kind of weight it by particles that are literally moving in and have a negative radial velocity. Very same qualitative results. Kind of any way you slice it, the cold mode gas is having more specific angular momentum than the other components. So this confused us at first. We weren't sure what was going on here. One way to kind of decipher what was going on, we decided to kind of zoom in on just one of our galaxies at a particular moment in time. I think it's about redshift 1-ish or so. So this is the same galaxy, 4 different views of it. On the top, you have just kind of 2 different orientations. The galaxy is basically edge on the left, and it's face on the right. So kind of the scale here in co-moving units here, 200 co-moving kiloparsecs. The galaxy itself is basically these red particles near the very center. And you can see it here face on. There's the galaxy. This is basically the virial radius at this epoch. And it looks from first glance, I've just like color-coded the points by like what their radius is, right? Okay, so real fancy. I didn't. These are color-coded by time since infall to the virial radius. So the cold mode gas, there's a very clear relation here. It doesn't take that long to sink down to the galaxy once it enters the virial radius. The stuff that fell in, less than 0.3 gigayears ago, it's out near the edges, kind of just making its way in. Notice it's not kind of pummeling straight in. It's spinning as it comes in, even at the virial radius. In fact, we found the kind of average angle of kind of entrance to the halo was like 30 or 40 degrees. This idea of, yes, the cold streams come in, but at least at this mass scale, they have enough angular momentum. They're kind of spiraling in even at the virial radius. They're not like pummeling straight down to the very, very center of the galaxy with 0 impact parameter.
So this is,
yeah.
It's 200 kiloparsecs across, is that?
Yes, co-moving, yeah. So the virial radius is kind of where the particles start here. And then as you kind of look at different time slices between 0.3 and 0.6 gigayears, those are the green particles. Between 0.6 and 1 gigayear is the kind of gold yellow particles. And then between 1 and 2 gigayears is the red particles here. And so you can see the kind of progression. Nice thing about SPH, you can just label the particles and literally ask what that particle did over time. And you can see it kind of flowing in. It kind of goes around once or so. You have this kind of disk-like structure that I'll return to in a second out here. Note the galaxy itself is more or less left and right edge on here. So the plane of this is not necessarily the exact same plane of the galaxy. There's some warp to this, as I think other simulations are finding as well. And now look down here. So this is just the gas that we kind of track it forward in time, and we know that it's going to make it all the way down to the galaxy without ever shock heating. It's the cold mode gas. Down here you have the hot mode gas. Very different picture. I mean, maybe if you squint your eyes, you could say there's some radial dependence. The stuff that just came in is still out at the outskirts. But beyond that, it's kind of a mishmash of all over the place. The only other structure you can really see is like you can kind of squint your eyes and see the galaxy itself doesn't have as much hot mode gas as the rest, and there's a little deficit there. But I mean, other than that, it's basically just pretty chaotic. It's all over the place. But also, the recent material is more likely to kind of come from down here, where the filaments are not. So the filament direction in this projection basically goes like that. So you can see that's where the cold mode gas is coming from. It's flowing in along the filaments. The hot mode gas is more kind of averaged, but it's coming in, not along the filaments for the most part. Yeah, there's the galaxy. So a couple of things we noticed just looking at this kind of figure in the simulation. The cold mode gas has a kind of spatially distinct supply of material. It's flowing in along the filaments, which I guess on further thought shouldn't be very surprising. But if it's coming in along a different physical structure, then it's going to have a different moment of inertia. It may not be surprising that the kind of angular momentum it gets from all these tidal torques might be slightly different than material that's physically coming in from different spatial regions around the galaxy. It's more coherent in structure. It has this extended structure. It kind of spirals in. Doesn't take that long to get to the galaxy, so there's a correlation between kind of the angular momentum it has as it builds the galaxy and gives it angular momentum. It's co-rotating roughly with the galaxy. Again, there's this warp, but it's spinning in the same rough way. And it's sinking pretty quickly. It doesn't spend that much time in the halo. Now, we'll get to some more kind of quantitative plots. Before we even get there, it's sinking quickly, and we just showed very recent accretion has more angular momentum than non-recent accretion, kind of as a kind of definition of how the spin parameter works, M-body simulations. Recent stuff always has higher angular momentum. So right off the bat, that's telling you if the cold gas sinks quicker than the hot gas, then you would think it should have, if you kind of look at all the cold gas in the halo, you're looking at recent stuff, and so it's going to have slightly more angular momentum than a kind of global average of dark matter, which can't go anywhere, or hot gas, which takes longer to sink. Yeah?
Where is the half angular momentum radius in this image?
The half angular momentum radius, I'm not sure I know what you mean. Like,
you can imagine thinking of plotting the angular momentum as a function of radius, just as on half mass radius, you can define it.
Yes, that's an interesting question. We haven't computed or looked at that.
Trying to understand the dynamical evolution of angular momentum and transfer angular momentum.
Okay, we haven't computed that. That's a good idea of something we should look at, the half momentum radius. And as I noted earlier, the infall is not purely radial. So sometimes we get this impression that filamentary cold mode infall has to be like zero impact parameter, tunneling straight down the barrel at the galaxy, which is not really what's happening. So more quantitatively than pretty picture, if you track the kind of sinking time, so we basically looked at once you enter the virial radius, how long does it take you to sink down to like a tenth of the virial radius? For our 4 different galaxies, again, as a function of cosmic time, obviously it's going to depend on kind of what redshift you're at. So the green lines are kind of the free fall time as a point of comparison, if you were just to free fall straight down to the center. The cold mode gas between 1 and 2 free fall times doesn't take that long to sink. The hot mode gas is roughly twice that. So it mixes more, it spends more time in the halo before it sinks down into the galaxy galactic region. And of course, the dark matter can't really go anywhere. It can't dissipate any energy, so it has much more elongated orbits. And if you kind of look at your average kind of accretion time for when the dark matter first fell in at redshift 0, then you get 8 or 9 gigayears ago as your kind of average when it fell in, as opposed to a few gigayears for cold gas that's in the halo. This is starting at redshift 0. The 3 gigayears, 3 gigayears is at redshift 0. It's much less than that earlier on. So this is redshift up here, 3 kind of down to 0. So earlier on, very, very short times. It's only at redshift 0 that you even get close to 3 gigayears. It's basically between 1 and 2 free fall times. So it doesn't quite just barrel straight down. It kind of loops around once or so as it comes in, and then it hits the galaxy. So again, for all of our galaxies, the cold mode gas in the halo is definitely probing the recent accretion. So this indicated maybe it's because it's coming along the filaments. Maybe that's why it has higher angular momentum. Maybe part of it is just that it's recent, but it's also kind of spatially distinct. Because even when you look at the very recent stuff, remember, I won't go back. But even when you look at the very recent accretion, for all of it, dark matter, hot mode, cold mode, you still had an excess in angular momentum for the cold mode accretion. So it's not just that it's recent accretion, because even the recent hot mode accretion has a little less angular momentum than the cold mode gas does. So it's kind of a point of comparison. If it really has to do with the spatial extent and kind of the way that it's structurally the way that it's coming in, what you could do, and what we did was we picked out basically the dark matter that was flowing in kind of from the direction of the filaments only. We basically kind of created kind of an opening, a cone starting from the galaxy, pointing towards the two filaments, and said, any dark matter that comes in that rough region and was accreted recently, we're going to call kind of filamentary dark matter because it's coming in from the direction of the filaments. Everything else we're going to call kind of non-filamentary dark matter coming in from everywhere else. And then we're going to compare to the hot and cold mode accretion and see if they're similar at all. Now, there's a whole bunch of scatter because that's not the most kind of robust way of kind of figuring that out. If you come up with a robust way of picking out dark matter particles that were filamentary only, please let me know. But again, one of our galaxies, as function of cosmic time, you have kind of the dark matter that flowed in along the filament, the dark matter that flowed in kind of from all over the place. It's pretty messy at high redshift because it's just so much more chaotic. It's hard to really pick out in any stable fashion, kind of filamentary versus not. But if you kind of make a eyeball comparison here to first order of cold mode gas coming in along the filament, hot mode gas coming in from kind of all the rest, then it kind of roughly tracks what the dark matter is doing. That the non-filamentary dark matter wiggles around kind of in the bottom of the plot. The filamentary dark matter wiggles around in kind of the top part of the plot. And you can see at least kind of to first order here, yes, the filaments are carrying more angular momentum than stuff elsewhere. And so kind of the filaments track the cold mode roughly, and the non-filaments track the hot mode roughly, and this kind of gives a little bit of an explanation of what's going on. The filaments are carrying more specific angular momentum at any given moment in time, material that's coming along the filaments. And it's kind of one of the things I mentioned in Kimedol, which used Ramses, I believe it was, and looked at a similar issue. It's basically like a lever arm effect. The stuff that's coming in the filaments right now, it had to kind of make its way over to the filament and then flow down at turnaround. If you track that material back, it had more specific angular momentum at that time. And so the filamentary material just in general at some snapshot is going to have slightly more angular momentum than stuff that's flowing in kind of from the voids. So one consequence of this, so you have this picture now where you have high angular momentum gas inflow in terms of the cold mode gas. It has very short sinking time, so it's not going to have time to really scramble itself in the halo because, of course, over time, the filaments don't come in along the exact same direction over long periods of cosmic time, but the gas only sticks around for a little while before sinking, so there's not a whole lot of time to disrupt that unless you have a major merger. So we have kind of coherent spatially, coherent in terms of velocity, co-rotating with the galaxy. It's set by basically the direction of the cosmic filaments, and so what we saw in our simulations, now not at every single time for every single galaxy, but in all 4 galaxies we kind of saw this effect that we labeled as cold flow disk. I think it's very similar to the extended rings that Avishai talked about yesterday, where here's a couple different redshifts, 1.6, 1.4, 0.7, 0.2. These are our 4 different simulations. And you can see its effect where, now again, this is 200 co-moving kiloparsecs, so the virial radius roughly sized, a little bigger than that. So the galaxy is at the center, and you see the kind of red-blue, this is line of sight velocity. See the kind of typical red-blue rotation curve of the galaxy. But the gas, this is kind of cold, dense gas, out in the halo, even upwards of 20, 30, 40, 50 kiloparsecs away, is roughly rotating the same way. And so you get these extended disk-like structures in all 4 of our galaxies. Now, it's not there all the time. It's not like every single galaxy in the universe is going to have a cold flow disk. But all 4 of our simulations have one at some point. It kind of has to do with a coherent inflow of not having a huge major merger recently, the streams not kind of changing shape and direction over the last few gigayears or so, and it kind of builds up this material. It doesn't stay there that long, so if you were to kind of cut off gas accretion, again, this would only stick around for a gigayear or so because the gas sinks very quickly, we already saw. But you can see this, and this is potentially observable. So actually before this, I had a couple papers where I talked about potentially trying to observe this in the kinematics of absorption lines systems. Of course, it's hard because you have to pick out what's inflow, and if you have a whole bunch of winds blowing stuff out, it may be harder to see actually in absorption. And you see these kind of for all 4 of our galaxies. You have this extended H1 disk structure co-rotating with the galaxy for 5 minutes. Okay. So it's present at some point in all 4 of our simulations, so it seems not uncommon, but not kind of universal. And so extended H1 disk, which is one of the things we were kind of worried about, is actually naturally falls out of a kind of better picture of angular momentum acquisition, because the cold mode gas has a lot more angular momentum, and it's easier to build a gas disk that's 2 or 3 times the size of the actual Milky Way disk if you're talking about recent cold mode gas accretion that's still on its way to the center. Okay, so a little bit about preliminary work, approved for all audiences. So one of the questions we had, it's very nice to know that like other groups in different codes are finding similar kind of angular momentum results. We wanted to look at how robust this is. So one project I'm working on right now is a kind of looking at the same initial conditions with different codes. Now, definitely different from the Agora project in that not nearly as ambitious, first of all. We don't have 100 million people working on it. But basically, we just wanted to look at kind of the 6 codes, Enzo, Ramses, R, Repo, Gasoline, Gadget. Pick kind of a popular or like well-used version of the physics. So the physics is all going to be different, and we're not going to be able to say anything robust about where the differences come in. Instead, we want to just focus on, is there at least something that they all agree on? So if you pick just kind of popular versions of the various codes, you run the exact same initial conditions. Is there things you can agree on? And specifically with the kind of with the robustness of different groups finding similar angular momentum results, what we are hoping, cross fingers, is that this picture of angular momentum growth, to what extent is that robust to the particular code you're using? Is it something that's going to change drastically if you work feedback a little different, or is this kind of an inescapable way of talking about how galaxies grow? Kind of as long as you have filaments, and as long as those filaments are feeding galaxies with cold gas, like there's not much you can do to change the way the angular momentum gets into the galaxy. Is that true or not? So we're starting with kind of, again, Milky Way-sized galaxy. Starting with the Enzo run from Young et al. 2010, so particle mass there, force resolution a little better than our past ones, 100 parsecs. So very preliminary, not all the simulations are done yet, a couple of them are, so very first look is comparing our kind of Enzo to Ramses simulation. Very early preliminary results, some of the main differences that we can't really talk about because who knows what's causing them. The hot halos are different. The precise morphology, that is like exactly when any given merger hits the galaxy, like is slightly different. So if you look at like redshift 2, the morphology is slightly different for the galaxies for the different runs in terms of like the timing of mergers has a big impact. But in terms of kind of your basic stellar mass growth, your basic growth in dark matter, the basic how much cold gas you have in the halo, the star formation histories are pretty similar. These peaks are just offset again because that merger happens slightly differently that creates a little starburst there. Are pretty similar. And so specifically looking at angular momentum, so first things that are kind of at very first look obviously different. The hot halo and outflow behavior. Outflow, of course, they have different feedback schemes. One's energy conserving, one's momentum conserving. So obviously you're going to get different results. Here's the basic structure. You can see the arrows are kind of the velocities, and here's a temperature map. So yeah, this one's blowing out outflows. This one's kind of mixing everything all over the place. Now again, the physics is very different in these. So like to try to pinpoint exactly which part of the physics is causing this, not the main point of our project, because who knows like what's exactly causing this, has probably something to do with the feedback implementation, obviously. But in terms of the cold gas, so looking at the cold gas in the halo here, slightly different projection, different temperature scale or density scale also. So you have density up here. Here's the Enzo versus Ramses. They're both roughly edge on. Unfortunately, the merger timing is slightly differently here. So this one's a little more chaotic right now. Basically, this guy made it in a little early in Ramses, and so he's already kind of messing up the galaxy. But if you look at kind of those plots I showed a second ago for the cold flow disks, kind of a line of sight velocity map. You can see very clearly down here, again, this is halo virial radius scale, that you have this, even at large distances away from the galaxy, you have this kind of red-blue, the streams are feeding the galaxy, roughly co-rotating in the same way and extending out much beyond the physical extent of the galaxy. A little harder to see over here in Ramses because there's these pockets of low density material. Basically hot stuff is flowing around here and there's not much cold. It's a little easier if we just look at the cold dense gas. So remove all the puffy stuff and just look at the dense stuff. So we're removing a lot of this. You see the same basic picture here. Here's the dense cold gas. Same thing down here. You have that nice red-blue kind of co-rotation, like the streams are feeding the galaxy signature. And it pops out much better in Ramses when you get rid of the low density stuff and you're not confusing yourself. Here's the cold dense gas. And again, the very central rotation, the kind of red-blue rotation curve. You see the same type of thing. Now these are very preliminary, as in I made these plots earlier this morning, so results may change. But at least to first glance, it's looking like this kind of picture of angular momentum growth to some level seems robust to different codes, and of course different groups are finding similar results, which is also encouraging. So how robust, to what extent, at what radius, etc. Kind of stay tuned, and we'll see what our results are as we look at more codes and in more detail. So kind of summarize kind of our main points here. So fresh accretion has 2 to 3 times more specific angular momentum than kind of a cumulative total. The cold mode gas, because it's flowing in along filaments, has higher angular momentum than kind of a non-filamentary accretion. It sinks very quickly, only a couple free fall times. Over long time scales, you get kind of vector cancellation. The streams don't stay in the exact same position all the time. Non-uniform infall mergers, et cetera, kind of mix things up. So by the time the gas gets down to the center and it gets torqued by the galaxy, it's lost some of that angular momentum, redistributed it. So you still get a decent spin parameter for the galaxy, not too high. And this whole scenario is more consistent with our modern picture of how galaxies form, instead of assuming like gas follows dark matter. And naturally pops out these kind of cold flow disks, which might be what we're seeing in these extended H1 disk observations. And this picture seems at least qualitatively kind of robust to different codes. More work needs to be in progress, but several other groups have looked at this, finding similar results, and we plan to compare different codes in the future to see how robust this really is. Thank you.
I think that qualitatively, the picture is very similar between our simulations and yours.
Mm-hmm.
There's one difference which I think has to do with your low resolution.
Mm-hmm.
And this is that all the rotation part in your case seems to be more extended. At least in this case, maybe it's a unique case. What we find more generically,
Mm-hmm.
with high resolution, that this cold flow disk, what we call the outer ring, is limited to 10 to 30 kiloparsec, namely 1/3 of the virial radius. And we don't see this rotating incoming stuff at the virial radius like in here. Instead, what we see is a transport along straight streams all the way to the inner halo. And I believe that in the pictures you showed already from Ramses and
Yeah.
it looks more similar to what we see in Henry. Straight inflow, and then most of the exchange of angular momentum happens in the inner halo.
Yeah.
Qualitatively, it's the same.
Yeah, and that could be a resolution thing in terms of how much the things are spinning as they come in. It's definitely one of those things too that just over cosmic time it changes slightly. So I said the average infall angle was 30 or 40 degrees, but it ranges kind of all over the place depending on exactly how the filaments are lined up. In terms of the extent, I would note that like our figure that showed 200 kiloparsecs, that was co-moving. So if you're looking at Z of 2 and you're talking about like physical 30 kiloparsecs, I mean, we're talking about roughly the same extent. 1/3 of the virial radius is about how far it goes out. And I would note too, like these, we call it cold flow disk, but it's not really a solid uniform disk. Even here you can see there's gaps in it. It's kind of like got the ring-like structure, but it's very full of holes. It's roughly doing that rotation as a whole object, but I think it's definitely qualitative agreement, very similar.
It's a very special case which you're looking at. You just showing us a very special case.
This is the most kind of straightforward to see what's happening example. But we saw those extended disks, maybe not quite this extended.
This one is on both sides. It falls from on different angles, but kind of like producing a rotating disk. This is what's unusual.
But I showed the 4 different panels of the kind of line of sight rotation curves that go out to much more than the extent of the disk. That happens in all 4 of our simulations. So I mean, maybe this is the prettiest example of it.
It has nothing to do with resolution because that material is coming with a cold filaments, right?
Yes.
And on those scales, you don't need to have good resolution. You don't need to have even hydrodynamics because it's coming with cold filaments in that way.
Yeah.
So why do you need to run Ramses and Snells? You just can't avoid it.
Well, one of the questions we want is, to what extent, if you have different feedback schemes, like will strong, hot winds flowing out, will those like compress these? Will they mess up this signal, or do you get it regardless? That's one of the questions.
Did you look at any dynamic and hot systems in your instant or in your zooms? It might be interesting to see what you think is different about the electric excretion or whatnot. It's things up, or if it's purely a major merger thing.
Well, it's not a major merger thing, because I mean major mergers aren't super frequent, and several of these were kind of set to not have a major merger for a long time, and they still have. So the angular momentum thing is more kind of a filament thing. Obviously, a merger can kind of spin things up as well. But actually, this example of it, the nice, pretty, prettiest version of the kind of co-rotating cold flow disk thing, this actually happens after a major merger really disrupted. It actually happened to be retrograde, which is unusual, and it actually disrupted the galaxy, and just the flows that came in after it really set this up because they were nice and coherent.
So M83's H1 disk has a diameter of about 80 kiloparsec. And so what I'm understanding is that none of your simulations produce something that has that extent for the H1 disk. Is that correct?
I would say we don't have one that has one to that extent, kind of at redshift 0. If you're thinking about, co-movement, at higher redshift, they have ones that are pretty big in terms of if you're thinking of co-moving units or whatever. But no, at redshift 0, we don't have. Yeah, we don't have a real physical extent of 80 kiloparsecs. Even that's pretty big. Yeah.
So let me push on that further. So M83, M101, there's a whole bunch of ones.
Yeah.
What I'm kind of curious about, though, is, let's take that this is how they form.
Sure. Just for sake of argument.
So the stuff that's at a third of a variable radius, is
Yes.
it also still plummeting in? Because what I'm wondering is in M83, M101, you actually see stars forming in them. If they're co-moving with the gas, it's actually forming stars on non-circular orbits as they're plummeting in, and that would be kind of interesting in terms of thinking about, you shouldn't see spiral structure, you shouldn't see kind of a disk. It's almost an in situ halo formation.
Yeah, in our simulations at the third variable radius, kind of as far out as that disk goes, it's spiraling in, but it's rotating to some degree, but it definitely has a radial velocity. It's falling into the galaxy as well. Again, it only stays out in the halo for 1 to 2 gigayears before it's kind of hit the disk. So it's constantly on its way in.
Cases and you see that it's much more in front of you. Some of your next slide.
In the
So, yeah, right.
yeah, so it's definitely falling in. It's not just going on nice circular orbits.
Okay, but going back to your discussion, is
Yeah.
it forming stars as it's falling?
Forming stars that's falling in, I wouldn't really trust our resolution to be able to answer that question one way or the other.
But M83 and M101 do.
Exactly, they're
But this is
I wouldn't think it would be. I mean, it's pretty dense gas. I wouldn't think that's crazy, but I can't really speak one way or the other.
The big stars only galaxies, little galaxies that come in with the stars.
I'm just saying that M101, M83, you see stars forming in those H1 disks.
That's a clear observation
Like we have
of
pictures
resolve that there are exceeded disks, but
H1 disks are just as
Dude.
orange.
I'm telling you that there are stars forming in those in local analogs. I mean, whether it's forming in this way or not, just M83's disk forms stars up to 80.
yeah, so you
140
see,
Yeah.
you see,
I'll show you a picture if you want.
in M83 and 101, it's not necessarily the case that it's, the star formation there is driven by this physical mechanism. It could be driven by perturbations from environment supplements, of course.
Mm-hmm.
But if this is the way that it forms,
Yeah.
then the prediction is that
Exactly.
those stars should be
Exactly.
forming on non-circular orbits.
This is
So
the
they're gonna
question
actually-
for those simulations.
Yeah.
It doesn't have resolution.
I mean, you could probably, like,
I'm asking in the context of if that stuff forms stars, if it's a non-circular orbit.
and depending on what winds you have, and if this is recycled material or what have you, like you might believe there's a prediction as well that if you have this inflowing stuff in this disk and it somehow does form stars as it comes in, that there should be kind of a metallicity difference. That this is more fresh cosmic accretion gas, and there should be observational signatures. If I don't know if that's what's happening, I wouldn't trust any statement about star formation in these things in the simulations.
I want to go back to Cameron's question.
Yes.
So I pulled up this paper, which I can't kind of reconcile it with this picture.
Okay.
This is Solace et al. 2011. They're looking at giving SP students.
Okay.
So I pulled it up and I just quote a sentence.
Okay.
So they say, according to morphology is the coherent alignment of the angular momentum of baryons that accrete with time. Spheroids tend to form and spin in a newly accreted gas that misalign with the galaxy. Disks, on the other hand, form out of gas that flows in similar angular momentum of earlier material. And the conclusion is gas accretion from a hot corona thus favors disk formation, whereas cold gas that flows in cold, favors the formation of spheroids. And this is how I reconcile it.
Now, so the presumption there is that cold gas can't be aligned or something over time? Because that's, I mean, I would say that's not what we're seeing, at least. Like, we're seeing the cold gas. There may be slight variations, but like the rough alignment of the cold gas doesn't like, I see we're not seeing that. I mean, it could just be the particular, merger histories, or I mean, I don't really have an answer to that, like why we're finding different things. Do you? Yeah. In terms of the alignment, what are those Milky Way size things too?
I'm really not familiar with this paper.
Oh, okay. I'm not familiar enough with that paper. Maybe we can look at it afterwards. It could be a mass scale thing, or yeah.
It's a deep.
Okay, so this is mostly work that I did over the last couple of years that was published last year. At the very end, I am going to show some fun work in progress, extremely preliminary, as in plots that were made earlier this morning, type preliminary results from upcoming work, and that'll be at the very end. So the story I'd like to kind of tell in the kind of canonical picture, or maybe now what we might call the old picture of galaxy formation. You have some kind of proto-galaxy at higher redshift. You have gas inflow from kind of all over the place. All the gas shock heats. The gas comes in with the same angular momentum as the dark matter, set from tidal torques on large scales. All the gas shock heats, it kind of mixes in the halo, just like the dark matter mixes in the halo. And so you still have kind of this same angular momentum distribution of dark matter versus gas. Well described by the halo spin parameter radius from the cosmic web, what's going on in terms of the angular momentum. Is there a difference between what the cold and hot modes of gas accretion are doing in terms of angular momentum? And therefore, is there kind of a more consistent model for how galaxies and galaxy halos in particular acquire their angular momentum? And this is all work that a number of other great teams are doing as well, with very complementary, similar results. Kim et al. Also has a paper. Avishai's talk the other day. They're finding similar things to kind of what I'm going to be saying today. So here's a pretty picture of a couple of our simulations, kind of zooming in. And now we're looking at things that end up as Milky Ways today. So we don't have the supermassive, living at a node where 3 or 4 streams all come together. These things kind of just sit in a filament. They're not quite as high mass and high kind of density peaks at high redshift. So more likely kind of sitting in a filament that's kind of flowing it from both sides rather than sitting in a node with lots of different streams intersecting. Roughly Milky Way size things. Gas resolution, the spatial resolution is a few hundred parsecs. These simulations are a few years old at this point. which again is why we're going to focus on the same spin as the dark matter. Doesn't really apply anymore. A couple more cuts kind of from the theory side. Observationally, there's been some observations of kind of more extended disk-like structures. So for example, from the Things survey here, you have a galaxy in kind of the H1. If you look at the size of the Milky Way versus the size of these things, they are huge disks requiring much more angular momentum. And so if you just had barely enough angular momentum in this old scenario to build a disk, and now you want to build a gas disk like 2 or 3 times as big, how can you possibly have that much angular momentum in your material? It just doesn't work if you start from the presumption that like all the gas has the same angular momentum distribution as the dark matter in your halo. It just doesn't work to build these things. The kind of more recent motivation from my own work, for a few years prior, we were looking at our simulations, and we looked at, this is the spin parameter in particular, but you should think of it just as angular momentum, as a function of time in one of our galaxies. And we see that, yes, the dark matter kind of wiggles around a roughly constant value, lambda, and then eventually some cold gas kind of cools out of this hot halo. And if you kind of keep track of the angular momentum and you look at the spin parameter of the dark matter, and the gas conserves angular momentum as it falls into the galaxy, you get something with kind of maybe just enough angular momentum to support a disk rotating galaxy. And this was kind of the picture we had in mind for how galaxies form. Now the problem is, a couple of problems with this kind of older picture. First of all, we know from simulations that's not how it works anymore, or we believe so anyway. Couple different scenarios. At high redshift, even if you have a massive halo and you used to think that everything's shock heated, we now know about these cold flows, cold mode accretion, and the gas is dense enough to stay cold and kind of penetrate all the way into the galaxy. So you don't have this mixing in the halo for longer time periods that you used to think that you had. You also have it kind of lower masses, kind of at all redshift, you still have this cold mode accretion. So this picture we have of the gas kind of acting the same way as the dark matter, and we've known that for a long time since N-body simulations. But if you looked at the gas in the halo, so not kind of blocking out the galaxy and just looking out in the halo out to the virial radius, the gas had much more angular momentum than the dark matter does. So you have kind of all the hot gas, kind of all the gas global average, just the cold mode gas, and you have much more angular momentum in the gas. So clearly, I mean, this should help in building these extended disks, but what's going on here? The old picture doesn't work because the gas is not doing the same thing as the dark matter. And so what's a better way to think of this? And that's kind of the goal of the paper we put out last year, studying the angular momentum acquisition in 4 zoom in, what was at the time high resolution simulations, and asking the following questions. How does the angular momentum buildup happen in the galaxy? Now, mostly we're looking at the halo. We don't want to try to say too many very strong statements about the galaxy itself, just for a matter of resolution and our feedback scheme that we have, which I'll talk about in a second. But in the halo itself, so when you're talking about like entering into the virial